Hello, my name is Shlomo Zilberstein, and I'm professor and director of the Resource-Bounded Reasoning Lab at UMass Amherst. We do research in artificial intelligence, studying how to build autonomous agents that can choose actions intelligently, operate reliably in unstructured environments, interact seamlessly with other agents and with people, all while coping with uncertainty, missing information, and limited computational resources. The planning problem involves an agent that perceives its environment using sensors and can take actions to change the environment. The simplest form of this problem, referred to as classical planning, is characterized by the blue labels, where the sensors are perfect, the environment is fully observable, actions are deterministic, and typically the problem involves a single decision maker in a static environment. Work in the lab has produced models and algorithms for the more general versions of this problem, characterized by the red labels, where sensors are noisy, the information about the environment is partial, actions are stochastic, and the problem may involve multiple interacting agents operating in a decentralized manner in a dynamic environment. We developed rich meta-reasoning mechanisms to control the planning process. Meta-reasoning is thinking about thinking, a reflective form of reasoning that helps you decide that you don't have enough knowledge to solve a particular problem, or that you spent enough time thinking and it's time to take action. Computers can do that as well by creating a meta-reasoning process that monitors and controls the planning process. Meta-reasoning itself could be treated as a planning process where the actions are various computational actions or the decision to terminate computation altogether. This clip illustrates the notion of belief space planning, planning using probabilistic information about the world rather than perfect information. This clip, created by former lab member Kyle Ray, shows a robot navigating from a start state to a goal state, while we see the belief it forms as it moves. At the top right corner, we see a symbolic representation of the domain used by the robot, with darker blue locations indicating a higher probability that the robot is at that particular location. The only sensory feedback is by touching a wall to confirm the location. Together with collaborators from Nissan Research, we applied belief space planning to autonomous vehicles, interacting with other vehicles and pedestrians at intersections. In this clip, also created by Kyle Ray, we see a vehicle approaching an intersection and the beliefs it forms about other vehicles and whether it is safe for it to cross the intersection. We have developed several new models and algorithms for multi-agent planning. The diagram shows the relationship between these models and well-known models such as MDPs and partially observable MDPs. Specifically, the decentralized POMDP model, DEC-POMDP, allows us to model multiple agents interacting in a collaborative setting, with each agent having access to different partial information about the overall situation. The POSG model, partially observable stochastic game, allows us to reason about similar settings where agents have different objectives or reward functions. In theoretical work, we were the first to show that the DEC-POMDP model is next hard, in practice showing that solving it optimally has double exponential complexity, even when two agents are involved. We also developed efficient approximation algorithms that exploit the structure of the domain to solve problems involving dozens of agents. Now, several current lab members will talk briefly about their research.
I'm Sandhya Sai. I'm a sixth-year PhD student at UMass Amherst. My research focus is on developing techniques for safe and reliable decision making in autonomous systems that operate in complex and unstructured real-world settings with potential interactions and collaborations with humans. One of my recent work is on overcoming the negative side effects of an AI system. This is based on observation that no matter how much effort or data are used to design an autonomous system, it must ultimately operate with an incomplete and inaccurate model of its environment. Consequently, there will always be undesired aspects of the system's behavior that a human observer would be able to identify. Negative side effects are the undesired effects of an agent's action that occur in addition to its intended effects on the environment. These side effects are unanticipated, undesirable, and inherently challenging to identify during system design. The key question is, how do we mitigate these undesirable impacts? One option is to entirely redesign the system to mitigate the impacts of its side effects and then go through extensive evaluation before redeploying it. In our work that was published at ICHCAI 2020, we present an alternate approach that allows the system to learn from feedback and update its behavior to overcome the negative side effects. We present a multi-objective formulation that offers a principled approach to balance the trade-off between optimizing the system's assigned task and mitigating its negative side effects. Our approach consists of three phases. First, the agent gathers data about the negative side effects of its actions using feedback. In the second phase, the gathered information is generalized to unseen situations by learning a predictive model of negative side effects and its associated penalty. Finally, the agent computes a negative side effects minimizing policy for execution. In recent work, we explore how to leverage human knowledge and assistance beyond providing feedback to mitigate the impacts of side effects. We formulate the problem as a human AI team with decoupled objectives. The agent optimizes its assigned task and the human applies minor modifications to the environment in order to mitigate the impacts of agent's negative side effects. This approach is simple yet effective because it is independent of the AI system's representation and learning capabilities. Furthermore, it also allows us to provide bounded guarantees on the agent's performance with respect to its assigned task and the occurrence of negative side effects. Our results show that this approach works well in mitigating side effects that are either avoidable or unavoidable when the agent is performing its assigned task in the environment.
Hey everybody, I'm Justin. I'm a fifth-year PhD student here at UMass, and my research focuses on a number of things in AI, specifically automated decision-making. This includes stuff like AI ethics, meta-reasoning for anytime algorithms, exception recovery, safety, and how to use state abstractions in decision-making models. Now, one of my most recent projects that we presented at AAAI this year was our work in ethically compliant planning. To give you some motivation, while it's generally possible to adjust the decision-making model of an autonomous system directly to try to make it be ethical, this can usually lead to unpredictable or unethical behavior. As a result, our goal was to enable an autonomous system to comply with a given ethical theory. So to try to do this, we proposed an approach for what we call an ethically compliant autonomous system. At a high level, the system has to complete a task while following a given ethical framework. The task is represented as a decision-making model, such as an MDP or a POMDP, and the ethical framework is represented both as an ethical context and a moral principle. The ethical context just contains all of the contextual information you would need to reason ethically, while the moral principle just tells you whether or not your policy is ethically compliant with respect to the ethical framework. Using these three components, we can tweak the objective of the ethically compliant autonomous system. On top of having the standard goal of finding a policy or some plan for acting in the world that maximizes the objective function of the decision-making model, we also want that policy to satisfy the moral principle of the ethical framework within that ethical context. As you can see on the diagram, this just means that the space of policies gets partitioned. Instead of just finding a policy in the green amoral region like usual, we now want to find a policy in the purple moral region. While I won't go into too much detail here, We also implemented simple versions of various ethical theories for our approach, such as divine command theory, prima facie duties, and virtue ethics, which was pretty cool to see in AI. Last but not least, we applied our approach to an autonomous vehicle domain. In this domain, an AV had to go from a start location to a goal location, where each street had different posted speed limits with either light or heavy pedestrian foot traffic. Based on this, the AV had to determine whether it should cruise lower than, at, or higher than the posted speed limit, based on the ethical theory that it had to follow. I won't go into the results here, but we made sure our approach not only produced a consistent price of morality, or how much cost is incurred to the task for being moral, but also generated optimal moral policies. Finally, we showed that our approach was easier to use and more accurate than standard approaches in a user study of planning and robotics experts.
Hey, my name is Connor Bassich. I am a fourth-year PhD student here at UMass Amherst in the Resource-Bounded Reasoning Lab. My primary area of research has focused on developing formal models and methods for enabling robotic systems deployed in the real world for long periods of time to better handle some of the key challenges that they face in these scenarios, including safe operation, approximate or underspecified models of the world, dynamic environments, and the like. In particular, the issue of safe operation can arise from the existence of an approximate or underspecified model of the world. The agent may believe that it is operating safely, but only because its model of the world is insufficient. To compensate for this, many real-world systems, such as autonomous vehicles, exploit the existence of humans who are effective at intuiting when certain actions are safe or not, but have no knowledge of the underlying models used by the autonomous agents. To tackle this issue, we recently developed an approach in a paper at AMAS 2020 for enabling autonomous agents to actively reason about their own competence as part of their planning model. We proposed what we call a competence-aware system, which is, at a high level, simply a system comprised of an autonomous agent, the robot, and a human agent, which we call the authority. The autonomous agent can have its autonomous operation restricted in various ways in different situations, and the human agent can perform assistive actions to, 1, keep the autonomous agent from acting in an unsafe manner when it is not actually competent to act autonomously, and 2, to compensate for the limitations in the agent's autonomy. This can be through direct override or teleoperation, etc. By learning its competence, something that is not known a priori, through interactions with the human authority, the agent can actually ultimately learn to optimize its autonomous operation. This model was actually tested on a fully functional AV prototype in collaboration with Alliance Innovation Lab, Silicon Valley. And some more recent work of mine has looked at taking this a step further. We don't just want the system to learn its current competence, we would actually like the system to improve its competence, the maximal extent of autonomy that it can utilize safely online during its deployment. And one way to tackle this is by refining its model of the world over time and making that more accurate and more in line with the model of the world that the human uses. To this end, we proposed an algorithm that improved the system's competence by increasing the granularity of its state representation through online model updates. This led to a more nuanced drawing of the boundaries between regions of the state space with different levels of competence. And we found that our approach was actually able to successfully identify key features of the world used by the human but were missing from the agent's planning model. And this significantly increased the competence of the system compared to a system without this capability.
Hi, my name is John Peterson. I'm a third-year PhD student in the Resource-Bounded Reasoning Lab, and my current work is on heuristic approaches for solving large, structured, stochastic shortest path problems. Stochastic shortest path problems are a class of Markov decision process which generalize shortest path problems in scenarios where actions can have multiple outcomes, and there's uncertainty over which outcomes will be observed when taking a particular action. Because of this, rather than computing a single deterministic path from start to goal which minimizes cumulative cost, we solve for a policy which is defined over all states that are reachable under our strategy, and which, in expectation, minimizes the cumulative cost of reaching the goal. In large SSPs, there are two main considerations we must contend with. The first is straightforward algorithmic efficiency. Heuristic search is a useful tool here, where we estimate the cost of reaching the goal from particular states in order to intelligently avoid searching in portions of the problem that are not going to be relevant to our eventual solution. The second is a representational issue, where in sufficiently large SSPs, even representing this probabilistic graph explicitly can become problematic. When there are large portions of the state space that aren't relevant to good solutions, heuristic search can again help us avoid generating them. But we have to be careful, since our heuristics might also need to represent the state space in order to be computed. Our strategy here is to compute heuristics over determinizations and relaxations of the problem in a representation more closely related to a compact symbolic representation. My current work's related to large SSPs where the problem requires structured information gathering during execution. We're developing approaches to intelligently compute heuristics for relaxations over certain kinds of subproblems that can then be combined in order to provide efficient and informative heuristics when problems have this particular structure.